Hi, my name is Kristín Jónsdóttir. I am a seismologist by training and I work here at IMO, the Icelandic Meteorological Office, as a team leader for natural hazard monitoring. And my responsibility here is the team that's doing the 24/7 natural hazard monitoring in Iceland. And the role of the office is to provide information about natural hazards in Iceland and provide warnings about impending hazards. So whether it is the weather, snow avalanches, floods, earthquakes, or volcanic eruptions. My responsibility is to make sure that the team that's doing the 24/7 operational monitoring is doing a good job, that they have everything they need, that they are looking at the right product and what they are producing is of good standards. Yeah, let's go and see what's inside the monitoring room. So we are focusing currently on the eruption, of course, that's ongoing on the Reykjanes Peninsula. And here we have a close-by web camera, but it is showing the current situation. It's very foggy, so we are not really seeing anything. But we know from the seismic data that there is activity ongoing. So this is the seismic tremor for the last 72 hours. And we see that there is repetitive activity in the crater. It rises and then decreases again. And there's nothing happening here for about 12 hours and then it starts to increase again. So we can see now that the activity is still high, but there's absolutely nothing to see on the web cameras. So this is why geophysical monitoring is very helpful when we are monitoring. We are also looking at the gas data from the eruption site. And what is important to notice about this monitor room is that we are looking at very different kinds of data and we are doing joint interpretation of different kinds of data. Let's look at the real-time monitoring data that we have. This is mostly, of course, earthquake, so seismic data. We have about 80 seismic stations in Iceland, and we are streaming the data. What does it mean that we are streaming the data? It means that since we measure something on a seismic station, we see it here on the screen 3 to 4 seconds later, whether it is next door or in Grímsey, north of Iceland. So all the data from the seismic stations is being streamed and there is a lot of automatic processing that is being done on the data. Here we are looking at the past 30 minutes, but over here we are looking at the past 10 hours. And what we usually align the seismic stations from north to south. So this is just to make it easier when we are looking at the screens, if something is happening in the north or in the south or about central Iceland. And also what we see here are different categories. So these are different frequency bands. This is something we call tremor data or RSAM data. So this is averaged seismic data to help us identify if there is tremor or earthquake activity. And the different frequency bands, they help us to identify what kind of activity it is. For example, if we see a spike on the lowest frequency, this may mean, and nothing on the others, this may mean that it's a teleseismic event. While on the highest frequency, if there's nothing or very little in the other frequency bands, it usually means it's a local tectonic event. On these screens, we are focusing more on what the current eruption in Fagradalsfjall. And here we've zoomed up the tremor or the RSAM data from the 2 closest stations. And again, we can see that there's an increase, so since midnight at the closest stations, signifying that there is eruptive activity ongoing in the crater. Now, we are not only looking at tremor data, we are also looking at earthquakes. And what we do with the earthquake data is that we locate the earthquakes. So here we are looking at a seismic recording from one station. The 3 lines here of vehicles, they show the 3 different components. So we have on the top the vertical component and then the 2 horizontal components. And clearly there's a nice phase here. So this is the primary wave for the P phase. And here we have the shear wave or the secondary S wave. And what the analyst does is just to repick the onsets of these phases. So for this earthquake, we have to go through all the seismic stations that have recorded the event and make sure that the arrival times are correct. And from the arrival times, we calculate a location. I mean, the data is different. For example, here at this station, we see a clear S phase, but no P phase. So if you look at the map here on the next screen, we see the location that has been found. So this is in South Iceland. And once we have reviewed the seismicity of the day, it's quite normal to have about 70 earthquakes per day. We calculate the magnitude of all the earthquakes that have been located. But there are more things than just the earthquake activity. There is, for example, river data that we are monitoring. So here we have a map giving us an overview of the status of rivers in Iceland. And we see here green colors, which indicate that we are having normal background levels of the rivers. But here in yellow and orange, we're seeing heightened water levels. So this is in Jökulsárfjöllum, a glacial river that goes from northern Vatnajökull. And there's increased levels there because of high temperatures lately. So information about this has already been sent. There's information on our website, and we've also contacted specialists about this. One more I would like to show you is here GPS data. So here we have a GPS station inside Grímsvötn, which is the most active volcano in Iceland. So this GPS sensor is actually inserted on the ice shelf, and we are monitoring the lake level. So there's a lake hidden underneath the ice shelf, and there's water being accumulated within the lake, and this is what we're monitoring here. And we might eventually expect a flood coming from this one. So different kinds of data that we're looking into. I've only given you some examples. It's a lot of data, it's a lot of work, and we are trying to jointly interpret what's ongoing here. But it's not only the persons that are sitting here that are doing this work. We have briefings every day at 2 o'clock where we have joint discussions with the different specialists, people that are looking at the meteorological observations, and we will call in other people if needed, even sometimes the civil protection or road authorities, to discuss specific things. We also practice contingency plans. So in case we see something that we are concerned about, we have contingency plans which we go to lead us through the steps that we need to take to inform the civil protection and the public. And we also we have weekly meetings with a bigger group here, and eventually, if there's something big going on, we will have a meeting with civil protection, and usually a science board is called in for to evaluate what's going on.
My name is Sara Barsotti, and I'm the coordinator for volcanic hazards at the Icelandic Meteorological Office. So when an eruption starts, we need to make sure that we can keep following the events, the phenomena that are ongoing, and in this sense also be capable to assess their hazards and their potential impact on the environment, on the surrounding. The IMO then needs to start to operate a complementary type of instrumentation and network that is in addition to the geophysical and geochemical network that Kristín has just presented. Why we need to make sure that we can follow what is happening in the atmosphere? That's because most of the time, along with an eruption, let's assume an explosive eruption at an Icelandic volcano here, we are going to see production of ash, so emission of injection of ash and tephra into the atmosphere, and consequently we will see tephra fallout, lightnings, and all this kind of phenomena. The IMO has the responsibility of informing properly and providing early warning for all the services concerning the aviation safety, as long as, of course, informing the civil protection about impending eruption and volcanic hazards. So one of the key elements in our atmospheric monitoring network is the radar network. So here in the image, we can see the current setup. Basically, we have 4 radars that are set up in the country. 2 of them are in the main airports, one in the southwest in Keflavik Airport and one in the northeast in Egilsstaðir. And then we have 2, in addition, mobile radars. These 2 mobile radars that can be moved actually closer to the eruption site in order to get a higher resolution information. These mobile radar, they are dual polarization. This means that we can ideally get information about the type of particles that are in the atmosphere, if either they are, their sphericity or possibly their shape. These are indeed instrumentation that are also used for the normal meteorological monitoring. So our forecasters that actually use this type of information for what concerns the normal precipitation or meteorological clouds. The location of the radar, indeed, they are actually close to where are the most dangerous, let's say, volcanoes in Iceland, or those from which we might expect explosive eruption and consequently associated volcanic ash cloud injected into the atmosphere. What we do with the radar data, one of the key information we want to assess, and that's a system that has been implemented here at the IMO, is the automatic process of the radar data in order to get the plume height. So how high into the atmosphere the ash or the tephra is injected. This system is called VESPA, and it is up and running for a variety of volcanoes. We can see that some of those that are the most dangerous, like Hekla, Katla, Grímsvötn, they are all active in this sense. So it is possible just to select one of those, and then we can see how the automatic process, this is showing the plume height as it is estimated by using the radar data from all the radar that they are seeing or covering the position of Grímsvötn volcano. And in this way it is possible, this is the 10 minutes average data. In this sense it is easily and quickly possible to get information about how high the volcanic plume is. When no eruptions are ongoing, this type of processing, of course, give us the information about normal meteorological clouds, so which is the height of the meteorological clouds in the atmosphere. The VESPA system that is currently running here, as said, on a daily basis, on real time, near real time, also allows to give a very initial guess about the intensity of the eruption. We know there is a direct link between the height of the plume and the mass eruption rate, so how much mass is released by unit of time. So the VESPA system indeed is integrating the automatic plume height estimates. It corrects it by the current meteorological data that we are downloading from the European Center, and this allows to get a very initial estimate of the mass flow rate. Of course, here the plot is currently empty, there is no explosive eruption ongoing, but that's the place where we are expecting then to see in real time the best guess or initial evaluation of mass flow rate. Another instrument that we use, that we have been developed so far in Iceland, that is going to corroborate or integrate the information coming from the radar network for what concerns the plume height estimates, are the calibrated web cameras. This has been already introduced by a video from Tal van Parny, but this is just to give an idea. This is how ideally this should look like. This is an example for the eruption in 2010 from the Eyjafjallajökull volcano. So the system will allow us to get almost in real time. So it of course depends on the frequency of the acquisition of the camera. Currently it is 10 minutes, but still to be capable to observe the plume and getting an estimate of the height once the image is corrected by the wind field, essentially the wind speed and the wind direction. Both this information, the radar data and the calibrated cameras, they both contribute in order to estimate the best information we can get as quickly as possible in order to define and characterize the intensity of the eruption we are seeing. And the final aim for this is, of course, to be capable to initialize, so provide this data in input to the dispersal model that eventually will help us in anticipating and predicting where the ash cloud will go, where the tephra fallout will happen, and which will be the intensity and the timing of these events. In addition to these sensors and instrumentation, of course, we use satellite products. The current eruption that is ongoing right now in Fagradalsfjall is a gas-rich eruption. It is featuring lava flows, and we are observing release of gas into the atmosphere. So this is an example. This is what we, on a daily basis, we see from the Sentinel-5P satellite. And this is the products that we are getting in order to identify the position and the intensity of the SO2 cloud. So the satellite view is, of course, a key information that allows us to, even in, I would say, in low visibility condition, where the cloud is, both on the near field, but also in the long range distance. So it is possible to identify where this cloud is traveling and which is its intensity. It is important to say about the web cameras, going back to that of course these are visible cameras. So once it will be dark time or during the night time, this is a limited usage that we can do with the web cameras, but the radar itself, it will be always running and always capable as long as the retrieval will be strong enough to tell us if, where and when there is ash in the atmosphere. Assessing the eruption source parameters like the mass flow rate of the plume height of the volcanic cloud is an essential element in order to be capable to provide reliable forecast of where the volcanic cloud might be traveling in the coming hours and where to expect tephra fallout. So here at the IMO we are running a set of numerical codes for a variety of volcanoes in order to be ready for any volcanoes erupting in the next hours, in order to be capable to say where and when the ash cloud will be hitting different areas. So here we can see the evolution of a volcanic cloud originating from Grímsvötn. This is an hypothetical eruption. Of course, Grímsvötn is not erupting today, but we are ready in case the eruption should start today in order to use the meteorological data from the day along with some predefined eruption condition in order to see again where and when we might expect the ash to be transported and eventually even to see where and how much the tephra fallout will be. So we can select which are the parameters. Colored are the concentration in the atmosphere, but in gray we can just follow which is the accumulation of tephra on the ground. This is of course important information for civil protection authorities in order to provide warnings and advices to the population living around and nearby the volcano. The IMO is the Volcano Observatory in Iceland, and in this sense we have the responsibility of disseminating information and providing as much as possible early warning about the volcanic activity and volcanic eruptions. In this sense, the IMO operates what is called the Aviation Color Code. That is a system that has been coded by ICAO, which is the International Civil Aviation Organization, in order to warn the aviation sector about which is the status of volcanoes and which is the hazard that volcano might pose to the aviation itself. So the color code is indeed shown in a map that we host on the IMO's website, where we show which is the status for all the 32 volcanic systems in Iceland. And as you can see now, we have most of them are on a green status. That means that they are just in what we call the background condition or the known background condition. So the volcanoes are not showing anything unusual or something unexpected. But two of them, Grímsvötn in the middle of Vatnajökull, is currently on a yellow status. And then we have here in the Reykjanes Peninsula the Krýsuvík volcanic system. It is on an orange. And it is on an orange because the eruption in Fagradalsfjall is currently ongoing. The scale goes from green to red, where red actually means the eruption is ongoing and there is a threat for the aviation. And that explains why Krýsuvík, despite the eruption is ongoing, is on orange. The current effusive eruption is not posing a real threat to the aviation. And for this reason, the decision by the scientists is that for the aviation color code, the proper color is orange. The eruption is ongoing, but there are no imminent hazard for the aviation and airplanes that are flying nearby the eruption site. All these things that we have been seeing today, they are regularly tested and practiced through exercises that we held almost each single month. So both the meteorologists on duty that are, of course, following the meteorological part of the response, together with the natural hazard specialists, they are practicing in order to go through what we call the contingency plans and be capable to remind and be quick in finding the right document, the right procedures, who to call in order to save time and allow that the response will be effective. Contingency plans then are checked almost each month through exercises. The aviation color code then is changed, so we are practicing how to decide how to select the different colors. And along with that, a VONA, which is the Volcano Observatory notification for the aviation, is sent out to the key users. So to summarize, the Icelandic Meteorological Office is the institution in charge of monitoring most of the natural phenomena in Iceland, and whenever possible to provide early warning and forecasting about impending hazards. The operational room is the core of the real-time monitoring, where an effective and efficient multidisciplinary work is done on a daily basis, where the natural hazard specialists work in strong collaboration with our meteorologists on duty. And the IMO works on a daily basis on a strong collaboration with the civil protection, our police, and the aviation stakeholders in order to support and provide a good service for the general public as well. If you want to learn more about how the operations works here at the IMO and how our systems works, then we could suggest you to follow all these references and publications here in the list that follows.